Okay, let us try to continue the geometric design of a highway. Now, we have just discussed before one of the horizontal curve in highways, which is your simple curve. Now, this time, let's proceed now to another horizontal curve in highway, and that is now your compound curve. So a compound curve, this is a curve formed by two circular or simple curves following one another and lying on the same side of a common tangent. Now, so you try to take note in here now that these are now your two. Okay, so these are now your two circular curves following one another, and they are lying on a common tangent. So they are lying on a common tangent. So let's try to determine now the elements of the compound curve. So still, we have to start with PC. So your PC in here is the point of curvature. So that is still the point of curvature. So this is the point where the compound curve, the curve leaves the tangent. So if you try to look at now the figure, so this is now the point where the first circular curve leaves the tangent. And another element of the simple curve is now your PP, which is known as the point of tangency. And this point of tangency is the point where the curve or the compound curve meets the tangent. Okay, so this is now the point where the compound curve meets the tangent. So we have the two simple curves in here, and then this circular curve in here meets the tangent, which is now the forward tangent. Now, let's try to consider this one in here as your V1. So V1. So this is your V1. So what is your V1 in here? Okay, so your V. I mean your V. So what is your V? So your V is the vertex. That is the vertex of the compound curve, also known as the point of intersection. It's the point of intersection of the two tangents. Point of intersection, or we call that as PI. So this is the vertex of the compound curve. So we now have, or also known as the point of intersection of the compound curve. Okay, so this is the point of intersection of the two intersecting tangents. Now, we now have your V1. Let us try to consider that this is now your V sub 2. So that the distance V1 V sub 2 is known as the common tangent. So this is your common tangent. So what is this common tangent? So this is the tangent. So we have the tangent where the two simple curves join. Okay, so this is not the common tangent, V1 to V2. So this is the common tangent. So this is the tangent where the two simple curves join. So we have the first simple curve and we now have the second simple curve. Now we have another elements of a simple curve is now your, okay, so we now have your PCC. So that is PCC. So what is this PCC? So your PCC, we call this as the point of compound curvature. So what is this point of compound curvature? So it's the point located at the common tangent. So we have the point located at the common tangent So that is the point located at the common tangent where the two simple curves join. Okay, so this is where the two simple curve joins. Okay, so your common tangent, so this is the four. Okay, so this is the tangent where the two simple curves, your V1, V2, where the two simple curves join. So V1, V2 is the common tangent. So this PCC in here is a point. So this is now a point where the two simple curves join. So this is the location where the two simple curves join. Okay, so we have other elements of the simple curve. Your I in here is the angle of intersection. So that is the deflection of the forward tangent of the compound curve. So there's one. And the other one is the tangent distance of the compound curve. So there are two tangent distance of the compound curve. One is on the side of the PC, which is now your T sub 1, capital P sub 1. And one is on the side of the PT, which is now your capital T sub 2. So your T1 in here is the tangent distance from the vertex of the compound curve to the PC of the compound curve. No, and this tangent is known as the back tangent. Your T2 in here is the distance from the vertex of the compound curve to the PT of the compound curve. And this tangent is known as the forward tangent. Now we have now the length of the compound curve. So the length of the compound curve is equal to the length of the first simple curve, which is denoted as LC1, plus the length of the second circular curve, which is denoted as LC2. And therefore, the total length of the compound curve is now equal to LC1 plus LC2. So we have another element of a simple, of a compound curve. So this is the long chord. So let's write that C, capital C. So that is the long chord of the compound curve. So the long chord of the compound curve, this is a chord. This is now the chord drawn from the PC to the PT. So this is therefore the long chord of the compound curve. So it is the distance drawn from the PC to the PT of the compound curve. And we denoted this one in here as capital C. Now we have another element of a compound curve is C1. So we now have your C1. So this is the long chord of the first simple curve. Okay, so the long chord of the first simple curve, this is the chord thrown from the PC to the PCC of the compound curve. So this is therefore your C1. Okay, so we now have your C1. So that is the chord thrown from the PC to the PCC. We consider that one as C sub 1. And another one in here is your C sub 2. So we have capital C2. So that is now the long chord of the second simple curve. And this long chord of the second simple curve is now the chord thrown from the PCC of the compound curve to the PT of the compound curve. So this is therefore your C sub 2. So the chord thrown from the PCC to the PT, and we denote that one as C sub 2. Now we have another element of a simple curve is now your R1. So R1 is the radius. So this is the radius of the first simple curve. So this is now the radius of the first simple curve. So this is the first simple curve. So we have R1. And another one is your R sub 2. So we still have your R sub 2, which is the radius of the second simple curve. This is therefore the radius of the second simple curve, which is equal to R sub 2. We still have other elements of the compound curve. So your I1. Okay, so we have your I1. So your I1 is the angle of intersection of intersection of the first simple curve. Okay, so this is the angle of intersection of the first simple curve. Let us consider that one as your I1. Or this is the central or the central angle of the first simple curve. So this is therefore the central angle of the first simple curve, or that one is now your I1. Okay, so another one is now your I2, and this is the angle of intersection of the second. So this is the second simple curve. So this is now your I2. So that is the angle of intersection of the second simple curve, and that is your I2. So this angle in here. Or the central angle of the second simple curve. So this is the central angle of the second simple curve, which is now your I2. So we have another element of the simple curve. So we have your small t1. So your small t1 is the tangent distance of the first simple curve. It's the tangent distance of the first simple curve, and this is now the distance measured along the tangent from the PC of the compound curve to the vertex of the first simple curve, or that is now your V1. And that is now your small t1. Tangent distance of the first simple curve. Now we also have your t2. So that is now the tangent distance of the second simple curve. Or this is the distance from the vertex of the second simple curve to the PT of the compound curve. So this is therefore your tangent distance of the second simple curve. We still have other elements of the simple curve, D1 and D sub 2. This is the degree of the first curve. First curve and the second curve respectively. Again, for on the first simple curve, the degree of the curve, so that is for a full length station again, is equal to D1. And for the second simple curve, the degree of the curve for a full length station again is equal to D sub 2. So that one is equal to D sub 2. We have some useful general formulas for compound curve. Now, supposing station V is given, so station vertex is given. Let us try to determine station PC. So your station of the PC is now equal to station of the vertex minus your t sub 1. That is minus t sub 1. Now, if you try to get station PT, do not get station V minus t sub 2 is station, or plus t sub 2 is station PT. You always have to go to where the compound curve starts. And the compound curve starts at the point of curvature, which is now your PC. Now, if you would like to determine now your station PCC, that is now equal to station of the PC plus the long chord of the first curve. So that is now the long length of the first simple curve. And to determine now PT, so your station PT is now equal to station of the PCC plus the length of the second circular curve. So that is on how to determine the stationing of these points in here when station V is given. Now, supposing station PT is given, station of the PT is given. So how are we going to determine station PC and station PI? So first, let us try to determine now your station PC. So station PC is now equal to station of the PT minus the length of the second simple curve minus the length of the first simple curve. So we always go to PC. And then if you are required to determine station of the vertex or station of the PI, so we now have station PC plus the tangent distance T1. So what is this tangent distance T sub 1? So your T sub 1 is now the distance from the PC to V1, or this is equal to the distance from the vertex of the first simple curve to the PCC. And your T2, small T2, is now the distance from the PCC to the vertex of the second simple curve, which is equal to the vertex of the second simple curve to the PT of the compound curve. So in other words, to determine the length of the common tangent, so the length of the common tangent V1, V2 is now equal to, so it's the length of the common tangent. V1, V2 is now equal to, okay, V1 to PCC, PCC to V2. And V1 to PCC is now your T1. And your PCC to V2, PCC to V2 is now your tangent distance of the second curve. So the length of the common tangent is now equal to the tangent distance of the first simple curve plus the tangent distance of the second simple curve. Now, let us try to consider triangle V1. We have now your V and your V sub 2. So this is V1, that is now your V, and that is V sub 2. So this is therefore your I1. And this one in here is your I sub 2. So I'm just going to consider this one in here is now your theta. Now, so if you try to determine the distance of the common tangent, which is V1, V2, so that is equal to T1 plus T sub 2. It's now equal to T1 plus T sub 2. Now, let us try to determine the distance, V1V and V2. So this is using sine law. So using now your sine law, so we have V1V is to sine I2 is now equal to V2 is to sine of I1 is now equal to T1 plus T2 is to sine of theta. So what is therefore your theta equal to? Now, if you try to prolong V1V, now this angle is equal to the angle of intersection of the compound curve. Hence, your theta is now equal to, so this is 180, that is equal to 180 minus the angle of intersection of the compound curve. Now, you try to take note in here now that for the solution of a compound curve, curves, refer to the specific and general formulas for simple curve. Again, you try to take this note in here. For the solution of compound curves, we refer to the specific and general formulas for simple curve, because your compound curve consists of two circular curves following one another and lying on the same side of a common tangent. Now, if you try to consider triangle TC, TCC, and TT. So we have your C1, we have your C2, and we now have the long chord of the compound curve. So we now have the angle included in the long chord of the first simple curve to the long chord of the compound curve is I1 all over 2, and for included angle of the long chord of the second curve to the long chord of the compound curve is I2 all over 2. And therefore, if you try to get now, your angle beta in there is now equal to 180 minus I1 all over 2 plus I2 all over 2. That is, I1 all over 2 plus I2 all over 2. Now, if you try to take a look in here now, that your I1 again as the angle of intersection of the first simple curve, and your I2 is the angle of intersection of the second simple curve. So how are we therefore going to determine the long chord of the compound curve? So that is now using cosine law. So using now your cosine law, your c squared is now equal to, we have c1 squared plus c2 squared. c1 squared plus c2 squared minus 2c1, multiply this one by c2 cosine of beta. How are we going to determine again the long chord of a circular curve? The long chord of a circular curve C is equal to 2r sine I all over 2. And this time, since we have two circular curves, so we distinguish this one with a subscript 1 and 2. 1 for the first circular curve and 2 for the second circular curve. Hence, your C1 is 2R1. We have sine I1 all over 2. And your C2 is equal to 2R sub 2. We have sine I2 all over 2. Two tangents intersect at station 0 plus 777.44. A compound curve laid under tangents has the following data. So we have your I1. So this is I1, and that is equal to 31 degrees. Your I2 is, that is now your I2, and that one is equal to 36 degrees. So if that is I1, this is also equal to I sub 1, and this one is now your I sub 2. Now, these two tangents intersect at station V, and the stationing of this, okay, the station at this intersection is at station 0 plus 777.44. Compute. So first, let's try to compute the stationing of the PC, the PCC, and the PT. Now, so first, let us try to recall, as what we have noted before, that for the solution of the compound curves, refer to the specific and general formulas for simple curve. Okay, so we already have taken the different equations of the different elements of a simple curve. So first, let us try to determine the radius of the first simple curve. So the radius of the first simple curve, knowing that the radius of a simple curve is equal to 1145.916 all over d. Since this is the radius of the first simple curve, so that is now your R1. So it's equal to 1145.916 all over d1. And that is equal to 1145.916 all over D1 is 3 degrees. And this is therefore equal to 381.972 meters. Your T1 or the tangent distance of the tangent distance of the first simple curve, which is now the distance from the PC to the P1, and that is now your T1. So your T1 in here is equal to R1 tangent I1 all over 2. So you notice again that this is the equation of a simple curve. So your R1 in here is equal to 381.972. We now have tangent of I1, so that is 31 degrees all over 2. So this is therefore equal to 105.93 meters. Next, let's try to determine the radius of the second simple curve, R sub 2. This is 1145.916 all over D sub 2. This is therefore equal to 1145.916 all over the degree of the second circular curve, 36 5 degrees. So this is equal to 299.183 meters. Now, the tangent distance of the second simple curve is from the V2 to the PT. So this is therefore the tangent distance of the second simple curve. So your T2 is now equal to R sub 2 tangent I2 all over 2. So this is equal to 299.183 tangent of I2, so that is 36 degrees all over 2, that is equal to 74.47 meters. So that is the tangent distance. This is the tangent distance of the second simple curve. Let us try to consider triangle V1, V, and V2. So this is your triangle V1, V, and V2. This is now your V1. This is the vertex or PI of the compound curve. And this is now your V2. So, I1 in here is 31 degrees. And your I2 is equal to 36 degrees. Okay, so we consider this angle before as theta. And your theta is now equal to 180 degrees minus I1 plus I2. So that is 31 degrees plus 36 degrees. Hence, your theta is equal to 113 degrees. So, let us try to consider now the distance V1 to V2. So your V1, V2, or the length of the common tangent, as what we had before, is now your T1 plus T2. That is T1 plus T sub 2. And this is therefore equal to, so your T1 is 105.93 meters plus your T2 is 74.47 meters. Therefore, the distance from the V1 to V2 of the compound curve is now equal to 180.4 meters. Okay, or this is therefore the length of the common tangent. Now, knowing now the length of the common tangent, let us try to determine V1V and VV2. That is now using sine law. Using sine law, then we have V1, V is to sine of 36 degrees is now equal to V1, V2 is to sine of theta, and theta is 113 degrees, is now equal to VV2. So we now have your VV2 is to, we now have sine of 31 degrees. So that V1V is to sine of 36 degrees is equal to V1V2 is 180.4 is to sine of 113 degrees. So your V1V is equal to 115. So we have 115.19 meters. Or V1V2, so we have V1V2, which is equal to 180, is to sine of 113 is now equal to VV2 is to sine of 31 degrees. So your VV2 is now equal to 100.94 meters. Okay, let us now determine the distance from TC to V, or this is therefore known as the tangent distance of the first simple curve, and that one is now your T1. So your T1 is now equal to, we have small t1 plus v1v. So that's v1v. Hence, your small t1 in here is equal to, your small t1 is equal to 105.93 plus v1v is 115.19. Hence, the tangent distance on the side of the PC or on the side of the back tangent is now equal to 221.12 meters. So let us try to determine now your LC1, which is the long chord, the length of the first simple curve. So from your simple curve LC is equal to 20I all over D. So for LC1, 20I1 all over D1. So that is 20. Your I1 is 31 and your D1 in here is equal to 3. Hence, this is equal to 206.67 meters. And your LC2 is equal to 20 I2 all over B sub 2. So this is 20 by I2 is 36 all over 3 degrees. And all over B sub 2 is 5 degrees. And this is equal to 144 meters. 144 meters. Now, let us then determine station of the PC, station of the PCC, and station of the PT. Station PC, station PCC, and station PT. Knowing now your station of the vertex or the PI, which is at station 0 plus 777.44. If you subtract T1, so that is now T1, and the value of T1 is 221.12. You subtract T1, you determine now, you can determine now station PC. Hence, station PC is at station 0 plus 556.32. Let's try to determine now station PCC. So we can determine station PCC by adding LC1 to station PC. So if you try to add LC1, and your LC1 is 206.67, then this is now station PCC. And this is therefore equal to 0 plus 762.99. Now, adding LC2, so this is now the length of the second simple curve. And the length of the second simple curve is 144. If you try to add LC2, then that is now your station PT. So station PT therefore 0 plus 906.99. So we now have station PC, station PCC, and station PT of the compound curve. So for letter B, if the PT is moved 15.24 meters out, compute station of the new PT with the PCC on the same point. Okay, so let us try to move PT 15.24 meters out. Okay, so this is just drawn in an exaggerated manner. So that is now your 15.24 meters with the PCC on the same point. So the PCC is on the same point. So if I will now going to prolong this one in here, this is now the vertex of the new curve. So this, I'm just going to consider this one as V3. So this is therefore, so we still have to draw the tangent line, and this is therefore so we have now this tangent line in here. So we move. So this one in here. So this stands in here. is 15.24 meters. Now, that is 15.24 meters. So, itong distance na to, that is 15.24 meters. Now, so if I will going to consider now this triangle in there. So, this is your triangle. So, this one in here is, so we have your, this is drawn. So, I'm just going to draw this one in an exaggerated manner. Now, such that this one in here is okay, so this is now your V sub 2. That is V sub 2. Now, this is now your V sub 3. So, we now have your, I did consider that one as V sub 3. Now, so at this time, this angle in here is equal to 36 degrees. So, that angle is equal to 36 degrees, which is equal to 36 degrees. So, this distance in here is 15.24 meters. So, that is 15.24 meters. So, that if you will going to get sine of 36 degrees, so that is 90 degrees. So, we have sine of 36 degrees, and that is now equal to 15.24 all over V2, V3. So, we now have your V2, V3 is now equal to 25.93 meters. That is 25.93 meters. So, let us try to determine now the tangent distance of the new curve. So, if you're now going to get the tangent distance of the new curve, so the distance from the original PCC, since PCC remains on this point or on the same point, so the tangent distance of the new circular curve, so that is PCC to V3. Or I'm just going to consider that one as T sub 3. So this is now your T3. So your T3 in here is now equal to, so we now have your T2, so that is now your T2 plus V2 V3. And this is now equal to your T2 before T2 was computed as 74.47 plus 25.93. So your T3 in here is now equal to 100.4 meters. So we have 100.4 meters. So that is now your T sub 3. So that your R3, therefore, from the equation again, the tangent distance is now equal to the radius of the circular curve. So that is now R3, tangent I3 all over 3. That is tangent of I3 all over 3. So your I3 in here is now equal to, so this is now, so if you try to prolong this one in here, your I3 is now equal to I sub 2. That is equal to I2, which is equal to 36 degrees. That is equal to I2. So this one in here, you try to take note. If you try to prolong that angle in here, so your I3, which is this one now. Okay, so that is now your I3, which is the same. This is parallel to that, and this is on the same line. And that is equal to 36 degrees. Okay, so we now have T sub 3 so is 104.4. So your R3 is now equal to T3 all over tangent I3 all over 3. All over tangent I3 all over 2. So this is therefore equal to T3, 100.4 all over tangent of 36 degrees all over 2. And this one is now equal to 309 meters. Is 309 meters. Next, let's try to determine now your D3 is equal to 1145.916 all over R3. That is 1145.916 all over 309. Hence, your D3 is 3.71 degrees. So we are now ready to determine your LC3. And that is 20 I3 all over your D3. So your D3 in here is 20. So your I3 is 36 degrees all over 3.71. And this is equal to, so this is equal to 144.07 meters. That is now your LC3. So hence, the new curve in here is now equal to, is now this curve in here. So this is now the new curve. Okay. So this is, okay, so the PCC remains the same. That is now the new vertex because we have to move PT 15.24 meters out. And this is therefore the new curve. Itong naka-black na to is now the new curve. And this is now your R sub 3. So your R sub 3 is now, this is now your R3. So that is V3. So this is therefore the new curve. And this is now your PT new. Okay, so that is therefore the new curve. And this is your ray R3. That is now your R3. So this is your PT new. So your station of the PT new, so station of the PT new is now equal to station PC. So what is station PC kanina? 0 plus station PCC 762.99. So that is station of the PCC. So I'm just going to add now LC3. And your LC3 is 144.07. So the station of the new PT is now equal to 194 pala. So this is 194.07. So this is 194.07. So this is station of the new PT is at station 0 plus 957.06. So this is just like as this one in here. If I'm going to place it in here now, so I'm just going to place it in there because there's no more space. So now that has been derived from here. So your station PCC is 0 plus 762.99. So, i-add natin ang LC3 which is 194.07 and therefore, that is now station of the new PT. So, this is now 0 plus 957.06. 0 plus 957.06. So this is now the station of the new PT.